It's said that in philosophy class, you learn about Plato. In this class, you're going to learn about Play-Doh. So now, and because it turns out Play-Doh is how we understand philosophy of ductile deformation. So we're now looking at ductile deformation. This can take several different forms. It can be compressional, or it can be extensional. We're going to look at a couple different forms that evolve when you get each of these different forms. So the primary way this manifests itself is through a process called folding. So we're going to start with some horizontal layers like we have the other couple of exercises, and now apply some folds. We're also going to erode those layers. So first type of fold, and again, folds typically result from compression, but they can, in some interesting circumstances, also take place during extension. Now, if you're in a purely ductile environment, you'll just stretch things out, and that can also be interesting. So the first type of fold is when you get a fold and it pops up into an A shape called an anticline. This is what it'll look like on the side. However, we live on a planet with an active atmosphere, and because of that active atmosphere, and so what you'll see is that crop pattern that looks a bit like this at the surface. You'll see it'll be depending on the exact nature of the anticline, it'll be somewhat either perfectly symmetrical or somewhat symmetrical. And so what you're seeing in the map view is the surface expression as a series of layers outcropping approximately like so. So if we do a let's try to think the differences now. Well, first of all, hopefully the stripes are starting to be obvious. Let's put them, dips point away from the axis. And then your dips are pointing from the axis of your fold. So what happens if the fold forms and or is turned the other way? There you go. So here, by the way, is an anticline out in the field before I go on. Now we get a syncline. Syncline looks like a smiley face. Yeah. Syncline. So now crop view, a syncline will look a lot like an anticline. You'll see this beautiful symmetric pattern of various layers outcropping at the surface. However, the subsurface, it's going to look a little different. And we have one powerful way on a geologic map to distinguish a syncline from an anticline. So recall the anticline, your dips were pointing away from the center. On your syncline, you still have your axis of, now, guess which way your dips are pointing? Away from the center. Oh, nice for that one. They point toward the center. Your synclines are going to dip toward the center. It's going to dip toward the center. Toward the center. So this is a nice way to think of your simple folds now. Now we're going to look at something a little more complicated because rare is it nature that you get a syncline that is perfect where the axis is running perfectly horizontal. Also, there's a couple other things that might happen during the folding process. For example, as we described in the event 1 scenario, we had overturned. This is in the case of very, very heavy horizontal compression. So far we've looked only at symmetrical folds. And for the purpose of this class, knowing there's folds that might be a little bit asymmetric is probably as far as we're going to go. But it's possible with further compression to get overturned folds. I'm sad that I'm folding. Actually have seat layers repeat themselves. This again is probably what happened with the event 1, that no longer is understood as a actual event. This is good, but now we're going to go a little bit more three-dimensional. So we're going to go a little more three-dimensional. If you look at the upper right corner of the screen, we're now going to take a fold. We're going to take a series of folds. Not only going to fold them, we're then going to incline them and rotate them off. There we go. So you see here, it's not very pretty, not the best example of this. You can sort of kind of see a little bit, is you're starting to see a little bit of an interesting pattern on this fold. So we call fold where the axis has tilted a plunging fold. And so in this case, you have a syncline over here and anticline over here. And now what you want to do is figure out, oh, what would the strike and dip symbols look like on this deal? Let's take a look. What do you have here now? Let's take a look. Let's take a look, see what kind of strikes and dips we might draw on this thing here. We'll just pull a little color schemes bars here, just so you can get a better sense where we're at on this map view at the top here. So we have the striking dips. So you see on the right side of the diagram, you got a plunging anticline. So remember, with the anticlines, your arrows are always, your dips are going to point away. A is for away, is for incline, is for arch. Syncline, you're going to have your dip symbols point towards the axis. Now, right along here, you have your axis for your syncline and axis for your anticline. In this case, it appears to be, you can see from the side here, plunging this direction. So we'll sometimes put on the axis of this little arrow indicating the direction of plunge. In this case, if north is up, it is plunging to the north. So here's another shot of that plunging fold in on map view. Now, what happens if you have, instead of a plunging fold, what happens if you have a place where all the dips are pointing away from the center? All the layers are dipping away from the center. You have something called a dome. As you can see, you'll see these sort of concentric outcrops. Now at the center, we'll have the deepest, the layer that was originally the deepest or the oldest. So here's your go sort of block. If you slice it on pretty much any way you slice it. You'll see your dips point away from the center of the dome. Perhaps my favorite specimen is one of these that you can quite literally see from space. To get there, we're going to take Google Earth all the way to the Sahara Desert. Maybe you'll spot it. You may have seen it on the internet. It certainly is a spectacular thing. It's in the nation of Mauritania. And you can see this from space. They call this the Eye of the Sahara. If you go down to Earth level, go down to the ground level, you can see these layers are tilting away from the center of this giant ring. Now, the textual name for this is the Richelieu structure. At least that's the name for this dome in this picture. But a lot of people prefer to call it the Eye of the Sahara. Does anyone know what sound an eyeball makes? See, see, see. That's the sound an eyeball makes. Hopefully, see, see. So what do you do if the youngest rock is in the center? Now we have something called a basin. What looked like an outcrop pattern, very similar to a dome. Except that now, and in rock model, anyway you slice it, you're going to see what looks like synclines. Difference is now with your dome, with your not dome, but with your basin, all your dips point towards your center. There we go. So get that in your notes. You get that the dome is dipping toward the center. And now we're going to take a little tour and see if we can find a couple domes. And trust me, there are plenty of them around the world, and they're visible from space, just like the just a dome or not. There are plenty of basins in the world. Let's take a look, see what we can find. So we are flying through northeastern Mexico on Google Earth, and we're going to fly right down to this thing right here. This is your basin by Caricitos. And so you can see, first of all, you can see a lot more beds. If you look closely, especially the best place to go is right where this little creek is, literally cutting through the basin. All the beds along here are dipping toward the center of this thing. You can see it really probably on this hillside here, where you have all these beds, all these flat irons, dipping towards the center. And that about wraps up the major structures that are formed by ductile deformation.